Hello and welcome to the first exercise to the lecture of Markus Diehl. So I will start with exercise 1 of lecture 1. And this exercise was about the QCD Lagrangian. And it was divided into different sub-exercises, subtasks. The first one was about the field strength tensor F mu nu and how to decompose it into these component tensors F mu nu A, which are multiplied with the respective Gell-Mann matrix TA. So let's derive the explicit form of this F mu nu A components. And I would say this is quite straightforward. So we take this definition, which I took from the lecture. So let's call it 1. And insert the decomposition of the gluon fields. So we insert equation 2 into equation 1. And what we get then, well, the first two terms are trivial, I suppose. So we have a del mu A TA minus del nu A TA. Next, we have the commutator. So let's write out explicitly both terms of this commutator. So we have an A mu B TB, A mu C TC minus IG A mu C TC A mu B TB. Okay, so why have I chosen the indices B and C? So this should be a C here. Well, it's quite obvious, I would say, after the next step. So having a look at these two terms here, we see that the field components A mu B and A mu C are simple numbers under SU3, so they are transforming the so that they're not matrices anymore. So the whole matrix content is given in terms of the Gell-Mann matrices. So we can factor out both of these fields, and what is left is the commutator of these two Gell-Mann matrices. Okay, so I'm saving a bit of time here by just so these first two terms, of course, remain unchanged. So what we have here is then the two gluon fields and the commutator of the Gell-Mann matrices. Of course, I should give them the right indices. Nu C TB TC. Okay, and next we can use the defining property of the Gell-Mann matrices. So this relation is what makes them generators of SU3. Okay, so let's use the indices in the right order here. BCA, TA. Well, and I would say that's it, because as you might already see, we have now a factor of TA in all of the three terms and can factor it out. So we have a del mu A mu A minus del mu A minus, so we have two factors of I here and here. That's the minus G A mu B A mu C F B C A T A. Okay, that's it. That's exactly the form we wanted. So we can define this factor here inside the brackets to be F mu nu A. Okay. That's all that we wanted to show here. So let's move on. Next exercise was about writing out the QCD Lagrangian in terms of explicit color indices and yeah, the fields with the respective color indices. So let's have a look at the first term. So we have a -1/2 trace of F mu nu F mu nu here. And that's quite straightforward. So we simply use the relation we already derived in the last exercise. So this gives us an F mu nu A, F mu nu B, trace of, okay, so just to be clear, need brackets here, of course, trace of TA, TB. And for that, we simply use the hint in the exercises in the lecture. So this is a 1/2 delta AB. And that's all we can do here. So we have a -1/4 F mu nu A F mu nu A. Okay, so you see we sum over color indices here as we should, because of course also the left-hand side has no open color indices, so the same should hold also for the right-hand side. Okay, first term. Second term. For the second term, that's the quark mass term, and the kinetic term and the gluon quark interaction term. There, let's write out the covariant derivative as I have shown you here. So of course, before we do that, of course, the quark field has this fundamental index I, which runs from 1 to 3. So the first term in the square brackets gives us an del mu delta ij plus ig a mu ij gamma mu minus mq. So here is so at this position here, actually what sits here is a unity matrix in color space. Of course, one can leave that out, but if we write explicit color indices, one should better also be explicit about that. And so that's the expression right here. So what you could then do, so we could stop here. What we could do is separate out the delta ij terms, which means that we can do a bit of simplification here. So we have then an del mu gamma mu minus mq qi. So a simple scalar product here of q and q bar. And the second term is a bit more complicated, but not too much. That's q bar I g a mu ij gamma mu qj. Okay. And again, that's all that we can do here. So let's move on to the next exercise. In this exercise, we want to show this relation. So I haven't given it here. So let's write it down. F mu nu is 1 over ij commutator of d mu d nu. So for this, we again need the explicit form of the covariant derivative. In this case, we're not interested in the color degrees of freedom, so let's ignore them for now. Of course, this again turns into an unity matrix, and yeah, so the color indices of the gluon field are kept implicit for now. That's not important for us in this exercise. So what we do is we insert this definition from above and use that the commutator is linear. So we got 4 terms here. Got the commutator of del mu and del nu. That's the first terms of both derivatives. And we have the mixed terms here. This is an ig del mu a nu and an ig a nu del nu. And the mixed term is ig squared and the commutator of a mu and a mu. Okay, we're almost there. Next, we use the relation that was given as a hint in the lectures. So, okay, so maybe let's repeat it so that everyone knows what I'm talking about. We have a del mu in the commutator with f applied on some other function g, and the hint was that this is equal to derivative acting only on f and then multiplied with another function g. Okay, so this means that the first commutator del mu a nu is equal to the derivative of del mu a nu. So I'm leaving out the brackets here. We actually have no function g that we could apply this on to. So in this context, it's not very important. But of course, one should always keep in mind that we're talking about operators here. So commutator of 2 derivative operators is of course again an operator. So ultimately, we apply this onto some function. But again, in this context, that's not that relevant. Okay, so that's the second term on the right-hand side above. The third term is the following. So we get an additional minus sign here, simply because we first need to switch the two components of the commutator. This gives us a minus sign, and then we can apply the identity from above. Okay, that's that. One should also keep in mind that the first term is a simple commutator of two partial derivatives. And of course, this vanishes because partial derivatives commute. Okay, so keeping all this in mind, we can further simplify this commutator. Which gives us IG. We factor out one factor of IG because we find it in all three terms here. And then second term is del mu A nu. Third term is del nu A nu. And we haven't talked about the fourth term, so this simply stays as it is. This is an IG commutator of A mu and A nu. Okay. And of course, let me scroll down one page up, no, 2 pages up, sorry. This is exactly the equation 1 of this first exercise. So that's the definition of the field strength tensor. So inserting it here gives us exactly what we wanted to show. Namely that the field strength tensor can be given in terms of the commutator of two covariant derivatives. Okay, and again, that's all that we wanted to show here. So let's continue with the last sub-exercise of exercise 1, which is the behavior of the QCD Lagrangian under SU3 transformations. So the relevant relations or the relevant properties under SU3 were already given in the lecture. I copy pasted them here in the first 2 lines. So let's again start with the first term of the QCD Lagrangian. This is minus 1/2. Let's skip that for now. Of course, minus 1/2 does not change under SU3 transformation. So the only thing that is important here is the F mu nu trace. Okay, so let's see how this transforms. Well, this first step is simply inserting the relation here above. And I'm also skipping the x arguments. They're also not important in this context. So what we get is precisely 2 sets of this UU dagger matrices on the right and on the left of the Fs. Okay, so that's what we get. And what we should see first is that this product here gives exactly the unity matrix. Why? Well, because again, that's the defining property of the SUN group. Okay. So that's actually trivial. Next, we use one of the most useful properties of the trace. namely that we can exchange the order of a matrix product by putting the last factor at the beginning or the first factor at the end. In this case, it's quite irrelevant actually, but let's do it this way. And as you might see, this here again gives us a unity matrix. So what is left is exactly what we started with. Trace of F mu nu, F mu nu. Okay, so this works. Then let's continue with the second term. So there we have the sum over quarks. Again, the sum over quarks is not relevant. I will actually prove to you that each term in the sum is individually invariant under SU3. Okay, so what we have here is this term then. How does this transform? Okay, but before we talk about that, let me show you one thing first. So what was actually not given here is the transformation behavior of Q bar. Okay, so let's have a look at this then first, because obviously we need it right now. Q bar, as you might know, is defined as the Hermitian conjugate of Q times gamma 0, because gamma 0 is a matrix in spin space, but not in color space. So this is transforms in the color singlet group. So that's a simple number as under SU3. So we're not interested in that. But how does Q dagger transform? Well, of course, this transforms as this transforms to U times Q, and then the Hermitian conjugate. And again, that's a relation, or a simple relation from linear algebra as the trace property. This gives us Q dagger, U dagger, gamma 0. So we switched the order of matrices under Hermitian conjugation. Okay. Then this means that Q dagger I d mu gamma mu minus MQ Q transforms as Q dagger U dagger gamma 0 I. How does the covariant derivative transforms? Exactly equal, exactly similar to the transformation behavior of F mu nu, which is somewhat expectable because F mu nu can be given as a commutator of these derivatives. Okay, let me check. Yes, U d mu U dagger gamma mu minus MQ. Again, quark mass is a simple number as under SU3. and Q transforms to U times Q. So what I forgot to say here is that this transformation behavior is exactly what you expect from an operator that acts on a vector space, which is transformed in this case under SU3, or yeah, a simple matrix actually. So you, of course, you know that we have this IJ components here. So this covariant derivative, and of course also the field strength tensor are matrices that act on these quark field color vectors. Okay, so back to this expression. Well, let's multiply both U dagger from the left and U from the right into this bracket so that we get a Q bar again on the left hand side. Then we have a U dagger U D mu U dagger U gamma mu minus MQ. Again, MQ commutes with everything because it's just a number. So we can write these two matrices together. And then we again have the defining property of the SU3 group, namely that all these products here give a unity matrix. And well, this leaves us with exactly the expression that we started with. Okay, sorry, this mu should be downstairs here. Minus MQ Q. And we see that also this term transforms to itself under SU3. Okay, so that's the full QCD Lagrangian. And we are done with exercise 1. So let's continue with the one loop diagrams. So most of the one loop diagrams were already given in the lecture, but I think it's a good idea to just derive every one loop diagram as systematic as we can be. So of course, there's this is a complicated task, and it gets quite complicated at 2 loop or 3 loop or 4 loop level, but at 1 loop it's still manageable. So I think that's the most systematic way to derive all one loop diagrams is well, to look at the building blocks, and the building blocks are given by the QCD Lagrangian, and they are the vertices. So we have the Quarks-Gluon vertex, we have the 3-gluon vertex, and we have the 4-gluon vertex. The first two scale with G, and the second one scales with G squared. So this will become important later. So then let's start with the quark propagator, which is at 3-level simple quark line, of course. So again, the most trivial thing you can do, let me check. This should come handy now. Okay. So of course, the most trivial thing you can do, and you should know that from QED, is simply attach a gluon here, which would be a photon, of course, in QED. And because we have nothing else we can do with it, we reattach it later. Later, of course. Do not take this too literal. So that's our first graph. Now's the question: are there more graphs? Well, we have used the first vertex, so let's have a look at the two remaining ones, and we clearly see that there's no possibility to draw any other diagram at one loop level. Of course, at two loop levels, what could attach gluon, for example, here? So a lot more crazy things are possible then. But for a 3-gluon vertex, we need 3 gluons, but we start with quark lines, so we cannot generate 3 gluon lines at one loop level. So that's all we have here. But of course, things become a bit more complicated for the gluon propagator. Okay, but you see that these two vertices look quite similar, and of course they produce graphs with the same shape. So we could draw here the analog of this quark propagated graph right here. And now things become yeah. So now we have a bit more. We have a bit more possibilities here, a bit more options. Okay, I got some. Sergio, can you still see my screen? Is everything all right?
Sure.
Okay, wonderful. I got some message here, but then that's not important. Okay, perfect.
I don't see problems actually.
Okay, wonderful. Okay, so let's compare these two vertices. You see that one 4-gluon vertex actually scales the same as 2 3-gluon vertices. So general rule is, what one could do in more or less every case, when you have 2 3-gluon vertices, you can contract one gluon line that connects these two vertices and get one 4-gluon vertex, and that's of the same order. That's the important thing. That's of the same order as our original 2 3-gluon vertices. So what we could do here is we can contract one. Oops, that's not what I wanted to do. We could contract one of these two gluon lines, either the upper or the lower one. In this case, this is actually equal because you get you get the same diagram out of both contractions. And what you would get is, so let's reduce contract this lower gluon line, and you see that these two vertices approach each other and ultimately form one 4-gluon vertex. So what we get is this graph here, which is sometimes called a tadpole. So that's the second graph we have. But of course, as I already told you, there's a third graph which is associated with the quark-gluon vertex. Well, so we haven't talked about quarks yet, but what we could do is start from this graph and substitute the two gluon lines in the middle for quark lines. Of course, that's perfectly fine. So you get two quark gluon vertices instead of the 2 3-gluon vertices here. And what you would then get is a Fermion loop in the middle. So you get this fermion running in the loop, a quark loop, of course. So instead of the gluon, now there's the quark running in the loop. Strictly speaking, you get one graph for each quark. So remember that the QCD Lagrangian here includes a sum over quarks, which means that you produce one interaction term for every quark, but they all look the same. So QCD does not, or quarks, QCD gluons couple to each and every quark in the same way. So what one almost always does is draw one diagram and just multiply with a factor of NF, where NF stands for the number of flavors, of active flavors. So you could be in a situation where you might want to exclude the top quark because your energy of this graph, or your energy is not large enough in the energy of the process, and then there's no reason to include the top quark. So that's second order effects. What you should take away here is that this graph here stands for NF graphs, each looking the same. So one gets a factor of NF here. Okay, so we've covered all three vertices, so there are no other options for us. Then let's continue with the vertices, so the vertex corrections, and start with the vertex, Foregluten vertex. Okay, so probably the most common diagram which one associates with vertex corrections is drawing this triangle here into this angle. So we get an exchanged gluon here. You have seen this diagram in some form many times in the lecture of Marcus. However, there are other options, of course. So one option is to trade this exchanged gluon right here for quarks. So we reroute the fermion flow now on this third side of the triangle. And the Foregluten vertex rule tells us that we need to attach then gluons here and gluons here. And of course, we need to have a gluon here. Okay, so that's of course also an option. And then there is nothing left. Let me check. No, nothing else. Okay, so of course, if you wish, we have covered both vertices now. The Foregluten vertex in this graph and the 3-gluon vertex in this graph. However, there's obviously no space to squeeze in a 4-gluon vertex. So we would need 4 gluons for that, but we cannot generate them at one loop level. So that's all we can do right here. And then the the second vertex is the 3-gluon vertex. And again, this behaves quite similar to the quark-gluon vertex to some extent at least. So, okay, so what we could do, of course, is mimic the first diagram and get a gluon here. What we could also do is then, of course, mimicking the second diagram would give us the same diagram again. So that's the degree of similarity we get here. So what we could do next, as we have done in the gluon propagator case, is we can contract 2 3-gluon vertices to 1 4-gluon vertex. So let's start here with this upper line. So we get this diagram then. So we have this 4-gluon vertex here. And of course, the gluon line attached here. And of course, we could do the same, just rotate it by 120 degrees and 240 degrees, 135, of course, 135. And, okay, so just by rotating this in this position here, so that this quark line, this gluon line gets in this position, and we could rotate this further and get this graph here. So depending on the application, these two graphs could lead to exactly the same results. However, if you break this rotation symmetry, for example, by saying, well, these two gluons are incoming and this is outgoing, it could be that these diagrams produce different results. Okay. So that's the 4-gluon vertex. What is missing again is the quark-gluon vertex, and also quite comparable to the gluon propagator. We get this quark triangle here. So again, we have this quark loop, which is proportional to the number of flavors running in this hidden in this vertex. So that's the third vertex. And again, we have covered all vertices in all combinations. And that's all that we can do in this case. So what was not part of the exercise, what was not covered in the lecture, was doing the same here for the 4-gluon vertex. So maybe let's quickly cover that. Of course, what we could have here is, for example, a gluon attached like this. Yeah, but again, this was not covered in the lecture, and strictly speaking, this is also not a one loop. Of course, it is a one loop direction, but it starts at one order higher in alpha S because this 4-gluon vertex gives you a G squared right from the beginning. So correcting it would introduce even more orders of G. So yeah, so that's a different order of alpha S here. So yeah, that was not that important in this context. Again, one has to find a way how to count these corrections. So of course, this is one loop correction, but at a higher order of alpha s. Okay, so that's all I wanted to say about exercise 2. Then let's end this class with exercise number 3. Exercise number 3 was about mass dimensions of the QCD Lagrangian and determining the mass dimensions of fields and also of the generalized coupling. Okay, so in dimensional regularization, many dimensions get shuffled around. So we are not allowed to say from the beginning, for example, that the mass dimension of the quark field is still 3/2. There's simply no good reason to assume that. However, what we are allowed to assume, and what we should assume actually, is that the action is still dimensionless. And you know that the action involves an exponential of an integrated Lagrangian, like this. Okay, so this directly implies that the mass dimension, I will always write mass dimensions with the square brackets. So the mass dimension of this integral here should be 0. Everything else wouldn't make sense in this context. Okay, and this will give us information about the mass dimension of the Lagrangian, because what we also know is that the mass dimension of a simple space-time dimension is -1, which means that the integral measure, the d-dimensional integral measure of x, has space-time dimension d, and this means that because so let's give this a star here. So this means that, let me put it this way. So the equation star is equivalent to saying the mass dimension of the integral measure plus the mass dimension of the QCD Lagrangian should be 0. And where we now know the integral measure of the mass dimension of the integral measure, meaning that the QCD Lagrangian should have mass dimension d. Okay, so that's our first result here. This will be very helpful. And of course, the QCD Lagrangian consists of many terms. But every term in this sum should then have the same mass dimension d. Okay, so we can start with the quark mass term, perhaps one of the simplest. So we start with the mass dimension of the quark mass term of some quark, not important here. Of course, every quark is treated in exactly the same way. So the mass dimension of the quark mass term is equal to 2 times the mass dimension of a quark field plus the mass dimension of a quark mass, which is very trivial, simply 1. And this should be equal to d. At this point here, we also use that the Hermitian conjugation does not affect the mass dimension. So of course, Hermitian conjugation operates on a whole different level than the mass dimension. Okay, so that's easy then. This simply means that the mass dimension of the quark field is equal to d minus 1 over 2, or writing out d, it is 3 over 2 minus epsilon. Okay, so of course, you know that d is equal to 4 minus 2 epsilon. Okay, so that's the first term. That's the first result. It will get a bit more complicated. However, let's simply have a look. So next we will talk about the first term of the QCD Lagrangian. Again, I'm leaving out the trace and the minus 1/2. This will change nothing in terms of the mass dimension. So we know that this is again co and contravariance have nothing to do with the mass dimension. So we can insert a factor of 2 here and only have a look at one field strength tensor. This is again D. So now we use the relation that we already derived earlier. We use that f mu nu is given in terms of the commutator of the two covariant derivatives divided by e.g. twiddle. Okay. Why this twiddle? Well, I think Marcus has already talked about this in the lecture. So in dimensional regularization, the coupling gets changed a little bit. He already gave you the formula for this, but we will derive this in a completely different way right now. So we assume that this coupling is in some form generalized, and what is important for us now is that this generalized means that we have that this coupling could also have a mass dimension. So that's the important part. Okay, so we can then reformulate this equation above by saying that 2 times the mass dimension of d mu minus the mass dimension of the coupling. So of course we divide by g twiddle, so this gives us a minus sign here, is equal to d over 2. Okay, well, then next, let's have a look at d mu. And d mu is del mu. Okay, let me have a look at the definition. So I'm not telling you any wrong signs here, plus IgA mu. Okay. Plus IG A mu. Okay, so we have again 2 terms here. We will concentrate first on the first term and then on the second term. The reason for this is quite clear, I would say. Well, for now, we don't know the mass dimension of, oops, I forgot a twiddle here. We don't know the mass dimension of A mu, so we should better not get any new unknown variables into our equation. The first part is quite easy. because we know that the mass dimension of a partial derivative is equal to the mass dimension of x to the minus 1, which is simply 1. Okay. So we can use that. We can use that here. So let's give this a red dot. So you know that we use the first part. So this gives us a 2 minus g twiddle is equal to d over 2. And this means that mass dimension of the generalized coupling is equal to, well, that's easy, 2 minus d over 2. And thus, this is nothing else but epsilon. Okay. And this is also what Marcus gave you in the lecture. For he derived this on completely different terms, but also derived at this equation that this G twiddle is the QCD coupling G times a factor mu to the epsilon, and this is exactly what produced this mass dimension epsilon here. Okay. Then okay, maybe let's give it a little red box here. Then next, let's have a look at the second term. So the second term means that we now introduce the Gluon field, but now it's our only unknown variable. So that's easy now to derive. So in this case, we have again a factor of 2, but now we have 2 times G twiddle plus 2 times AU. No? See, we have a factor of G twiddle here and a factor of A mu here, minus mass dimension of G twiddle is equal to D over 2. Okay, so this factor here cancels with this here. And this means that mass dimension of A mu is equal to D over 4. No, let's see what I've done wrong. No, should be correct. Yes, should be correct. D over 4 plus G twiddle, and inserting both D and G twiddle, we get. Oh yes, I forgot a 1/2 here. 1/2. Sorry, 1/2. So we get an 1 minus 1/2. No, plus 1/2 epsilon plus 1/2 epsilon. So we have a, okay, maybe one step so that you can all follow me. 1 plus 1/2 epsilon, that's 4 plus 2 epsilon. Okay, I see it's an, okay, so okay, of course. It's a minus sign here and also a minus sign here. Okay, so now I'm correct, right? A mu is D over 4 minus 1/2 G twiddle. D over 4 is 4 minus 2 epsilon over 4. This is 1 minus 1/2 epsilon, okay? Minus 1/2 epsilon, and this is 1 minus epsilon. Okay, so that's our last result. And I think what was also part of the exercise was a little cross-check. Okay, so not explicitly, but I think it's quite instructive to have a look at the last at the last part, which we did not consider until now, and this is the quark-gluon interaction term. So we have this Q bar here, then this covariant derivatives gives us an A mu, and this Q here. And of course, this covariant derivatives also gives us a G twiddle. So for our derivations to be consistent, this quark interaction term should also give us the correct result. Okay, so we have this Q bar here, G twiddle, A mu, G. So I'm leaving out the gammas and the i's and whatever, everything that has no mass dimension. So this here, well, let's have a look. We find two quark fields. This gives us two factors of Q. This gives us also one G twiddle and one mass dimension of A mu. So let's insert everything. Mass dimension of Q was 2 times 3/2, which gives us a 3. And also 2 times minus epsilon. This gives us a -2 epsilon. Mass dimension of G twiddle is a plus epsilon. Mass dimension of A mu, just one line above, is +1 minus epsilon. This is 4 minus 2 epsilon. And this is D as it should be. Okay. And let me have a quick look. Yep, that's all I wanted to say. So we derived the mass dimension of the quark field and of the gluon field and of the generalized coupling simply by demanding that the action should be dimensionless. So in practice, what you will always see is these factors of mu to the epsilon that accompany the QCD coupling G. And you see that this is actually consistent with the underlying theory. So I think what Marcus did was this was more like an ad hoc assumption that one should have this additional mass dimension, and because otherwise things like he had a logarithm with a dimensionful argument, and this wouldn't have made any sense. So he said, okay, let's introduce this factor mu to the epsilon, and then everything works out. And you see that this factor actually is consistent with with the underlying QCD theory when applying dimensional regularization to it. So everything is consistent, everything is as it should be. Yeah, and I think that's the take-home message from today. So yeah, that's it. Thank you very much. And yeah, that's all I wanted to say.
Thank you very much, Dorian. Extremely clear, detailed, clean. So we are very happy. And we will see each other for the next exercise sessions in the next days. Thank you. Bye-bye.
See you.
I
Goodbye.
close the session.